All right, I think it's time. Welcome back. We do have homework due tomorrow, and our test is on Friday. A little something to look forward to, think about. So tomorrow we will just do review type problems for the test. I hope that was helpful last time. I felt like last time maybe I gave you too many. Were there too many? I felt like during class time people didn't get very far, but maybe it was mostly helpful afterwards. I don't know. All right, we'll see how many I can come up with. I might give you less just because I can't think of that many. But the test will be just on the new stuff. So since the previous exam, which I believe is quotients, and then continuous functions, homeomorphisms, and a little bit about metric spaces. So just through what you will see on the homework for tomorrow. Any new stuff that we do today, if any, will not be on the test. All right, we'll talk more about it next time. Before we get started, I thought I might tell you a little bit about, I don't know if you've heard about the big news in mathematics over the past week. There was a big discovery made last week. Sorry, Julie's already heard this once before today. But a big discovery in the area of, it's called aperiodic tiling. I don't know if you've heard of this. I had a nice chat with my kids about this because this is something you could easily impress a middle schooler with, and maybe even younger than that. Aperiodic tilings of the plane is something that people have been thinking about this since like the 70s at least. There's a famous example of this called the Penrose tiling, which is a tiling of the plane. That means like you just sort of lay down shapes on the flat plane in a way that covers the whole plane. Like one of the simplest ways to do that would be just like using squares. You can certainly tile the entire plane using squares, but this is periodic. This is periodic. It's not aperiodic. So periodic meaning this is a repeating pattern. Aperiodic would be a way of tiling the whole plane with shapes so that the pattern never repeats, which sounds like maybe that's not even possible or not even sensible. But actually it is possible to tile the whole plane using tiles in a way which never repeats. And the Penrose tiling was kind of maybe the first, I don't know about the first example, but popular example discovered in the 1970s, I believe, using two shapes. And a lot of university math departments, just to be cute, like the floor of the math department is often tiled in a Penrose tiling, which it doesn't look like much if you aren't paying attention, but if you look carefully, the Penrose tiling is made up of two tiles of two different shapes, but it has no periodicity. That is, the pattern that you make out of them never repeats itself as you spread out across the whole plane, which is kind of, that's interesting. Anyway, the big news, which was just publicized, just announced last week, is that a group of 4 researchers have discovered the first ever what they call aperiodic monotile. That is one tile of one slightly weird shape, where when you lay it down, you can cover the whole plane in such a way that it's aperiodic, no repeating pattern. So I will show you a picture, which I happen to have here. You can make this your computer background. This is the aperiodic tiling discovered by these guys. So it's just this one shape, repeated over and over, I don't know if when you look at it you might feel like, isn't there some kind of pattern to where the dark ones, it's the same shape, they're just coloring it to emphasize certain things about the pattern, which is to say there actually isn't a pattern. It is not a repeating pattern in the traditional sense. but it does cover up the whole plane. Using only one shape, that was the big deal. People have been looking for this since, like I said, the 70s, but not able to do it until now. This shape here they called the hat, because I guess when you look at it in this orientation, it looks like a hat. Although it's been a bit controversial. Some people think it should be called the T-shirt, which when you draw it that way, it looks more like a T-shirt. You do have to use reflections of this. If you look carefully, I believe the white ones are reflections of the dark blue ones. You can see this T-shirt has the little thing on the right side, and it's on the left side on this one. So those are mirror image reflections. So you do need to reflect that shape, but otherwise it's just the same shape. Rotations and reflections of that same shape. It's a big whoop. There was an article in the New York Times about it yesterday, or this weekend at some point. So it's not often that the New York Times covers abstract mathematical discoveries, but this is even cuter to put as tiles on the floor of your math department building. Any thoughts or questions about it? I think it's interesting. Check it out if you're interested. On the aperiodic monotile. There's already people who've made 3D models of this. You can 3D print yourself 100 of these and lay them out on your floor or something. Pretty cute. All right. We've been talking about metric spaces. This has nothing to do with metric spaces. I don't know, maybe it does. We're talking about metric spaces, and specifically metric spaces and how they relate to topological spaces. Metric spaces, I will say, versus topological spaces. If you have a metric space, can you make it into a topological space? And then vice versa. If you have a topological space, can you make it into a metric space? And we've talked about, or we were sort of in the middle of talking about one of those directions, and that was sort of metric space and converting or turning it into a topological space. That is to say, can we use the metric to create a topology? And the answer is yes. When you say create a topology, you have to describe to me what are the open sets. And if you have a metric, you can use the metric to create the balls. And those balls are the open sets in the topology. So that's the basic idea for converting a metric space into a topological space is, can we use the metric to create a topology? The answer is yes. We can define the ball around x of radius epsilon. This is, the definition, and this is all y such that the distance from x to y is less than epsilon, right? So we define that, and then we just say that is an open set, and that's what makes our topology. So we define these and then use the balls as basis neighborhoods for a topology. And there's a word for this, or a phrase that I actually didn't say this last time. This is all review from last time, but here's something that I didn't say this time. This is called, there's a name for this topology. It's called the topology induced by the metric. That is, it's the topology that you get when you use the metric to create neighborhoods. If you use the balls as basis neighborhoods, then that's called the topology induced by the metric. So we have several different metrics, like we talked about before, several different metrics for R2. There was the standard metric, there's also the taxicab metric and the maximum metric. You can get the topology induced by the standard metric. You can also get the topology induced by the taxicab metric, and so on. All right, any different metric will give you its own topology by using those balls. Okay, there was one bit of details that we were talking about last time that I want to finish. We were kind of like in the middle of talking about the details last time. We need to demonstrate right here. I said use the balls as basis neighborhoods. We need to demonstrate that the balls actually have the appropriate properties to be a basis. So I want to prove that, and actually we did sort of the hard work of this last time. What remains is pretty straightforward, but we need to show that the balls make a basis. And if you recall, there are two properties necessary to be a basis. But can I just remind us, first of all, last time we proved very specifically, last time we had a lemma, which we're going to have to use. This, that was the point of the proof that we did at the very end. We're going to use as part of this, showing that the balls make a basis. And the lemma said that if y is in the ball of around x of radius epsilon, then there exists delta greater than 0 such that the ball around y of radius delta is a subset of the ball around x of radius epsilon. This basically just says you can, if you have a point inside of a ball, you can make a smaller ball in, that's around that point inside the big ball. So if you have sort of a big ball, which is the ball around x, but then you have some other y in there, that other y has a smaller ball around it. That's what this says. The ball around y of some smaller radius is a subset of the ball around x of radius epsilon. All right. So we did the proof of this. You can prove this. Of course, on the picture there, it's obvious, but that picture is drawn using the standard metric in R2, which is, we don't want to assume that. This, you can prove this using basically only the triangle inequality, not using any standard metric in R2. All right, anyway, that was from last time. We're going to use this at a certain point. Can we show that the balls make a basis? I'll write this as a theorem. The balls make a basis. This you should not feel you have to remember for the test because it's kind of an old topic, but does anyone happen to remember there were two properties of a basis? Anybody remember what they were? You should probably remember this for the final exam, but yeah?
Remember one of them was like a shrinking property.
Yeah, one of this, that's the second one, which is the more complicated one, is a shrinking property. That's actually what the lemma is going to be used for. Anyone remember the first one, which is much easier? Remember, the idea of a basis is that it consists of a bunch of simple open sets. Yeah, the basis sets, first of all, they have to cover the entire space, and then also they have this shrinking intersections property. So the first is the covering property, and this you just have to demonstrate. I will say we want to show that any x in the space is inside a basis set. So we say something like, you know, let x be a point in my space x, then x is in, can you say what ball is x in? You just have to say specifically that x is actually inside a ball. Anybody want to suggest? There's not just one correct answer, but there's probably one answer that everybody's going to say, yeah? Yeah, I don't want to, what is epsilon? She said ball, x is always in the ball of x with radius epsilon. That's true, although I would rather say this in a specific way, not using, yeah? Yeah, how about ball of x with radius 1? Why did I say 1? Because, I don't know, you got to say something, right? Don't say 0, that there is no ball with radius 0, but any non-zero positive number there will work. This is why I said there's not just one correct answer, but this is basically the answer that everybody should say. There's no reason to say anything other than that. All right, so let x be in the metric space, then x is automatically in this ball. So that means that the covering property is satisfied. All right, that's the easy one. And then the second one is this shrinking intersections property. which is kind of complicated, although all the hard work is done by the lemma in this example. So the intersections property, this is the one, sort of the picture that you should have in mind is if I have two balls like this, and there's a point in the intersection, then there exists another ball which is totally inside of the intersection. All right, that's the idea. So I'm going to say let's say these two balls are the ball around x and the ball around y. I have to just make up two different radii. So I'll say let the ball of x and radius epsilon 1 and the ball around y of radius epsilon 2 be balls with some intersection, and the intersection is not empty. So typically the way you say this is there is some other point inside of the intersection. I'll call that one, this point in the middle, z, say. So let these be balls with z in the intersection. Ball of x, E1, intersect ball of y, epsilon 2. All right? And then our job is to create another ball that is completely inside of the intersection. And how do you know that exists? Well, it's basically the picture from the lemma, right? Now, the lemma says that you can make a ball which is inside of one other ball. Does that mean you can make a ball here which is like inside both of these balls? I think it does. It just means, first of all, I choose the radius small enough so that it's inside this ball, and then I make it even smaller so that it's also inside of this ball. That's the basic idea. So what I will say is something like, by the lemma, there exists some delta so small that small enough so that that little ball is inside of both of those two balls. So small that ball of z comma delta is a subset of ball x epsilon 1, and also ball z delta is a subset of ball y epsilon 2. All right. The lemma says you can make one ball inside of another ball. That means just by doing the lemma twice, if you like, you can make one ball inside of both of them. All right, but that means that the ball, if I said it's a subset of this one and it's also a subset of this one, that means it's actually a subset of the intersection. So ball of z and delta. All the points in this ball are part of this set and also part of this set. So that means that all the points of this ball are in the intersection, and that's the basis intersection property that we need. All right, that's the appropriate property for the basis intersections shrinking property. All right. Excellent. Any questions about that? Really, the most of the work is done by the lemma from last time. Great. So the moral of the story here is, so any metric defines an induced topology. And if you do have a set with several different metrics, that means you can use those different metrics to create different topologies. For example, in R2, we had, D, the standard Euclidean metric. We also had the taxicab metric, also the maximum metric, and we also had the discrete metric. All right. What are the topologies that are induced by these various things? Well, if I just sort of have a set here, maybe I'll make some kind of a blobby set without its boundary. This is like a circus peanut shaped set. First of all, is that set open using the standard D? Is it open using D, that is to say the standard Euclidean metric? Is it open using the standard Euclidean metric? That is to say, remember the way to tell something is open I mean, there's many ways, but the typical way would be if you choose any point in here, x, is there a neighborhood around x which is contained inside the peanut? If I'm using the standard metric, that means when I say neighborhood, I'm talking about round balls. And is it the case that there's a round neighborhood around x that's inside the peanut? The answer is yes, it is. So is it open using D? The answer is yes, since any point in there has a standard ball around it. I will say a standard ball contained in the set. That's the typical way to check if a set is open or not, is does each point have a small neighborhood around it that's inside the set, all right? So that was using the standard metric. What about one of our other metrics? So what about, is it open using DT? In this case, you have to think about what do the balls look like using the taxicab metric. Does anybody happen to remember? We did this last time. I had you draw little pictures. Yeah. Yeah, the taxicab balls look like a diamond shape. So they're not circles, but they are things like that. This is what a typical ball looks like. This is a DT ball. All right, a taxicab ball looks like that. Is this set still open? Is it still true that you can fit a taxicab ball around it? Yes, you might have to make it a little smaller. No, actually, the taxicab ball is already smaller than the round balls of a certain radius, right? You just, because this is smaller than a circle. So anyway, is it open using the taxicab metric? Yes, for exactly the same reason. Actually, when you're talking about whether a set is open, it doesn't matter if you use we talked about this before. It doesn't matter if you use perfectly round balls or this other kind of shape. This is a diamond-shaped ball. So here we can also put taxicab-style balls around any point. All right? Actually, if you think about it, I think you will agree, there's nothing special about this sort of peanut-shaped set. It's always true that if a point has a round ball around it, you can also make a diamond-shaped ball around it, right? The moral of the story is the metric induced by the standard, the topology induced by the standard metric is the same as the topology induced by the taxicab metric. That is, if you use standard balls versus taxi balls, it doesn't change which sets are open versus which sets are not open. And that means the topologies you get are the same. So I will write that down. The topologies induced by the standard metric, D, versus the taxi metric, DT, are the same. Even though the individual balls look different, they have the same results when you want to ask, does a point have a little ball around it which is inside of this set? They create the same open sets. So I will say the balls look different, but they create the same open sets. All right, so these are two different metrics, but they give me the same topology on R2. What about the max metric? Remember that one? Is this again the same thing, or is it really different? Anybody recall what are the bowels? What do the bowels look like for the D max metric? They look like little squares, yeah. So here the balls look like squares. Is that any different, or is it the same thing again? I think it's the same thing again, right? I mean, the balls look different, but they would create the same open sets regardless of whether you use a diamond shape or a square shape or a circle shape. It doesn't matter in terms of defining open sets. All right, so again, this again is the same topology. All right, so those three metrics, they are different as metrics, and that you might say they are geometrically different. That is to say, when you actually measure distances, you're going to get different answers. You measure the distance between 2 points in these three different ways. But topologically, they end up being equivalent to one another. And so if all you care about is the topology, then really there is no difference between the three metrics, although there are many, many different examples where it's not all you care about is the topology. All right. I think I mentioned, if you are looking at sort of driving distances, you don't care about the standard Euclidean distance between 2 points. You care about the distance along the roads. And if you say, well, I don't care about that at all because all I care about is the topology. Really, the topology doesn't tell you anything about distances at all. It would just say, all you can say topologically is like, there is a route from one point to the other, which is not interesting at all from the point of view of driving directions. Okay, this again gives me the same topology. How about the discrete metric? I don't know, this one you might feel like is a little different. D, the discrete metric. Remember, this is the one in which all points are judged to be distance 1 apart, except for a point in itself is always distance 0. What do the balls look like in the discrete metric? Yeah. Yeah, just individual points. So here the balls look like individual points. So is that peanut-like shape an open set using the discrete metric? There's almost nothing special about this specific shape. But if I take, again, a point here, x, is there a ball around x which is totally inside of that set? The answer is yes, because x by itself, you can just use that single point as the ball. So this is open using these discrete balls. But actually, since you're allowed to just use that point by itself, I would say also something like the peanut with its boundary points, even if you chose x right on the side there, this is still open. Because I can use x as a ball by itself. So this is open, since just that set is a ball. And so this set, you can put a discrete ball around x that's totally contained in the set. All right. Actually, if you think about it, every set will be open. It doesn't even matter what the set looks like at all. If you choose any point in that set, that point by itself is a ball, and so it automatically can work like as its own neighborhood. So actually, all sets are open using that discrete metric, because every point can just be used as itself for its own neighborhood. And so the ball will always be contained in the original set. All sets are open using the discrete metric. In other words, what I'm talking about is the discrete topology. That's why this is called the discrete metric. The discrete topology is the one where all sets are open. So to say that in a fancy way, D, the discrete metric, induces the discrete topology. Because if you use the discrete metric to create your balls, then what you get is the discrete topology from that. It all makes sense. All right. We got 20 minutes left. I think it's plenty of time. I actually had a little something for you all to try. This might be a little warm-up for the test warm-up tomorrow. Pre-warm-up, warm-up. I thought it might be fun to see, this would probably make a good test question, although I'm using the word Hausdorff, which is kind of an old topic, but I hope everybody remembers. I would like for you all to try This is a theorem about metric spaces that's important. Any metric space is Hausdorff. That is to say, when you start with a metric space, the topology that it creates is automatically a Hausdorff space. I hope you remember what Hausdorff means. It means if you have 2 points, x and y, then you can create neighborhoods around each one that do not overlap one another. The points are housed off. I went to a conference over the spring break, and I was talking to people there. You know, and we were mostly topologists there. And I said, hey, you guys ever hear this? Hausdorff means housed off. None of them had ever heard that before. And I thought that it was silly. All right. Any metric space is Hausdorff. See if you can demonstrate that. So you have to demonstrate that if you have 2 points in your metric space, and this is not all that difficult, you have to demonstrate that you can make a neighborhood around each one where the 2 neighborhoods don't overlap, and all you're allowed to use is the metric, right? You don't use the standard geometrical arguments or anything like that. You just have to say how to get these 2 open sets using the metric. All right? Think about it. See what you think. This would make a great mathematical baby name, wouldn't it? Hausdorff. Really, this is what you need. You need to just find those 2 open sets and create them somehow using the metric. I'll give you a hint.
distances would
You can use the metric as part of your defining what the sets are. As I'm walking around, I see many people stuck at the same point, which is basically what I wrote here. How do you decide how? So one thing that I saw, people said, what should the sort of center point of these balls be? They should be X and Y, right? So it's the U should be the ball around X with radius. Well, that's the issue. What should I choose to be the radius? I want to choose the two balls so that they don't overlap. Yeah?
Could you possibly make it the metric distance from X to Y divided by 2?
Yeah, this is what I would say. Like these 2 points, they have a particular distance, which is determined by the metric. And then I want the radius of each of those balls to be that distance over 2. Actually, then the two balls would kind of kiss right in the middle, but that's okay because they don't include their boundary points, so they still would not have any overlap. Yeah, so this is what she said. Distance from X to Y over 2. Distance from X to Y over 2. Yeah, those are, so on the picture actually, the true picture that I made is more like this, where the two balls are actually just barely touching, but that's the total distance over 2 is what each of those radii are. Now, is it clear that all of this business is true? So it's definitely clear from the definitions that X is in U and Y is in V. That's because these are balls around X and Y. So I will say, just move this over here. So just to make sure it all works. So X is in U and Y is in V. Is it really true that U intersect V is the empty set? Now, according to the picture, I think it's obvious that there can't be any point which is in both of those balls. But actually, I think it bears some discussion of in detail why exactly are those two balls disjoint. By the way, what I might have expected you to come up with on a test or a homework, if this was a homework question, probably this would be good enough, and you would say something like, they're obviously have no intersection between these two balls. Although I think it's a good idea to think about this. Can we actually demonstrate why there is no intersection? So now I want to show that U intersect V is the empty set. Why I think it's worth discussing is, like, for one thing, actually nothing that I've said so far uses any of the 3 properties of being a metric, which is allegedly what this whole thing is about. Like, you can show that it's Hausdorff using only the fact that your metric is symmetric, positive, definite, and transitive, and not transitive, triangle inequality, right? So can we prove this using only the properties of a metric, which is the positive, definite, the symmetry, and the triangle inequality? So for here, I'm going to do a little proof by contradiction. I think is the easiest way to work this out. So, so I will say, to get a contradiction, assume that Z is some other point inside the intersection, right? Now this is not possible, but this is what we're trying to demonstrate, that this intersection is empty. So to get a contradiction, I assume that there is something actually in between. And then can we somehow show that this violates either the positive definite or the symmetry or the triangle inequality? So a picture apparently of this would be, I have this ball of radius, can I just say d over 2? It's the total distance divided by 2. And then some other ball. Now, I'm imagining somehow that Z is in both of these, which really is not possible, but this is another ball also of radius d over 2. Can we somehow see a contradiction here? This is X, this is Y. I don't know about you, but I feel a certain urge, a certain impulse when I'm talking about a metric and I see 3 different points, x, y, and z, my gut instinct is to do something like the triangle inequality, all right? So can we somehow phrase this in terms of the triangle inequality? That would be the distance from x to y versus distance from x to z and the distance from z to y, right? So I will say by the triangle inequality, you know, can I just write the distance from x to y is less than or equal to the distance from x to z plus the distance from z to y, right? That's what the triangle inequality says. What can you say about each of those distances? The distance from x to z and the distance from z to y? I'm going to sort of replace this using you can't say what it equals, but you can give it a inequality. I would say because z is inside of this ball, what does that mean about the distance from x to z?
Less than the distance over 2.
Less than, yeah, distance over 2. So this is less than d over 2, which is really distance x to y over 2, right? And then what about distance from y to z? Is the same thing, right? Z is also inside of the ball around y, and so the distance from y to z is also less than distance x, y over 2, all right? Anyone see the contradiction with that? Yeah?
Like the 2 added together equals the distance from x to y.
Yeah, right. You just add these guys up and it equals distance from x to y. And now we've shown that distance x to y is strictly less than distance x to y. And that's the contradiction. All right. So it really is all about the triangle inequality. Yeah?
Wait, isn't the triangle inequality less than or equal to?
Here? Yeah, but this one is straight up less than. So that means that, like here, these may be equal, but these are definitely not equal. So when you read the whole thing through, it's a strict less than. Yeah, great. So any metric space is automatically Hausdorff. That's the moral of all of this stuff. There are other nice properties of metric spaces. So I will say in general, metric spaces are topologically nice. Because they are Hausdorff and for other reasons, they are Hausdorff and other nice properties, which our book actually does a lot more about metric spaces that I don't want to do because I want to move on to some other stuff. But they are Hausdorff and other nice properties. All right. There are lots of nice properties of metric spaces that we don't have enough time to get into. I would like we got like 7 minutes left, and this is enough time to talk about the other way round. What we've been talking about lately was topological spaces versus metric spaces. And so far we've shown that any metric space any metric can be used to define a topology, but I want to talk about going the other way around. So any metric induces a topology by using the balls as the basis neighborhoods. Can we go the other way around is what I want to discuss in our remaining 7 minutes. That is, if you start with a topology, can you use the topology to create a metric function? All right. This seems, in my opinion, much harder to try and do that. If you start with a topology, that is to say, I tell you which sets are open and which sets are not open, can you somehow from there create a function, like a real valued function, which is a metric which satisfies the triangle inequality? That to me sounds quite a bit more complicated than if you start with this function, building open sets out of it. If you start with open sets and try to make the function out of nowhere, that seems a lot harder. And the answer, you know, because I said we can do this in 6 remaining minutes. The answer is no, you can't go the other way, not in general. So that is to say there are some topological spaces which don't have a metric that corresponds to their open sets. And the simplest example, well, really, it's because, I'll give you the short version, we already said all metric spaces are Hausdorff, but we know there are some topological spaces which are not Hausdorff. That means those ones, they cannot have a metric, all right? So you can't go the other way in general. Among other reasons, all metric spaces are Hausdorff. So, for example, something like R with the finite complement topology, if you recall, this is not Hausdorff, and therefore it cannot be a metric space. That means there is no metric function you can use that makes that topology. So this is not a metric space. That means it is impossible to make a metric function which gives you that topology, the finite complement topology. All right, a fancier way to say that is R, the finite complement topology, is not metrizable. That means this space, in my opinion, the way that I think of that is this space is so weird that you can never describe it by measuring distances. It has a topology which is not expressible by measuring distances, which, in my opinion, is pretty weird. All right. Also, it's also true that the trivial topology, that's the one where the only open sets are the empty set and the entire space. That also is not metrizable. Trivial topology is also not metrizable because it's not Hausdorff. Right? You might ask, okay, these ones are not metrizable because they are not Hausdorff. Is it a fact that every Hausdorff is automatically metrizable? The answer to that is no. There are some weird examples of Hausdorff spaces which are still too weird to be metrizable, but they're kind of weird. There are theorems about which topological spaces are metrizable and which are not. And the most famous one is called Urysohn's metrization theorem, which is in the section of the book which we are about to skip. So if you're interested about which things are metrizable and which are not, you can read about it if you like. Like, that is something that people care a lot about, but not me, I suppose. It's important, but there are other more important things for us to talk about. All right, I think that'll do for metric spaces as a whole. Next time we will start up with something completely different, but before that we'll do the review and then the test. So I'll see you all tomorrow. We do have homework due tomorrow. Let me know if you got questions about it. I would be happy to discuss.